Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on July 31st, 2025, so about 5 days ago. This paper introduces a new method that can stop up to 100% of backdoor attacks in fine-tuned models, with a false positive rate below 1.2%. The paper is titled, Watch the Weights, Unsupervised Monitoring and Control of Fine-Tuned LLMs. And, as we'll see, the technique can also be used to uncover a model's hidden fine-tuning priorities. It also proves highly effective at verifying when a model has supposedly unlearned something and can even steer the model to recover that information. And the authors themselves took to X to break down their findings, and the thread is getting some good engagement. They highlight the key problem with current approaches. They have a blind spot because they depend on the specific data you use to test the model. This new technique instead looks directly at the model's weights. As one user aptly put it, why interpret activations when the weights themselves hold the signal? It's a powerful and simple observation, and really gets to the core of the idea. Also, the authors shared their official code, and if you check out the repository, you'll find the full implementation. It includes a quick start guide and code examples for running both the anomaly detection and the intervention methods we just discussed, which is really cool to see. Alright, so this figure really illustrates the core concept we've been talking about. On the left, you see the problem with traditional methods that look at activations, which are basically the model's internal signals. When you have very few examples of a threat, those signals get lost in the noise. But now look at the middle panel. This new method analyzes the model's weight changes directly. It uses a technique called singular value decomposition to find a behavioral direction that cleanly separates normal from anomalous behavior. And the results on the right show it detects 100% of backdoors. So this algorithm here details the nuts and bolts of how the method works. First, this top procedure calculates the weight difference and uses singular value decomposition to extract the key behavioral vectors. Then, this middle function acts as a hook. It monitors the model's internal activity, and if that activity deviates too much along those behavioral directions, it flags the input. And in what's called steering mode, it can even push the activation back to a safe baseline, effectively neutralizing the threat. Okay, so to really put their method to the test, the authors set up a comprehensive suite of experiments, which this table lays out. They test on a whole range of models and tuning methods, from LoRa models to models tuned with what's called poisoned reinforcement learning from human feedback. That's a process where the model's safety training is deliberately corrupted to sneak in a backdoor. And they test it against different kinds of anomalies, from harmful content with secret triggers to specific topics like Harry Potter questions. And this table shows a direct comparison on those PPO models. They tested their weight watch method against two baselines, one that looks at activation differences and a black box method called beat. The numbers are pretty stark. The weight watch method in this column achieves nearly 100% detection on all the Trojan backdoors. Meanwhile, the beat method over here fails almost completely, often detecting 0% of the attacks, which really highlights the performance gap between the approaches. Now, moving beyond just backdoor detection, this table shows the method's performance on unlearning, which is when a model is trained to forget specific information. And the results are really strong. For a model called Circuit Breaker, it flags over 95% of completions related to these erased topics. And, importantly, the false positive rate, the chance it flags a normal prompt by mistake, remains incredibly low, under 2% across all tests. This shows it's not just sensitive, but also highly precise. And this steering capability isn't just for defense. It can also be used to actively recover forgotten knowledge. This table shows this on a model called Zephyr RMU. You can see that after the unlearning process, performance on the biology and cyber benchmarks drops significantly. But look at this last row. By applying more aggressive steering, they recover most of that lost performance, especially in biology, pushing the score from 31.2 back up to 56.2. And this happens with almost no impact on general knowledge. So to wrap up, by analyzing the weight differences between a fine-tuned model and its base, this method provides a powerful, data-free way to monitor and control LLMs. It's a huge step for detecting hidden backdoors and auditing models. That's it for this episode of the